Thank you all for coming here after some break. And it's my great pleasure to introduce Dr. Andrew Craig from University of Johannesburg. Andrew has a doctorate from Oxford from 2012. He was also doing a lot of rowing in Oxford, and as a curiosity I would mention that in Oxford he was rowing with the twin brothers Winklevoss, whom you might remember from the movie Social Network as the inventors of Facebook. So they know each other. Andrew's areas of expertise are lattices, lattice theory, logic, universal algebra. This is his third visit to Slovakia and Banská Bystrica, so it's a great pleasure to have you here again at our department as a guest. And today Andrew will talk about what might be considered actually as the problem, the open problem number one in universal algebra, and it's the famous finite lattice representation problem. So Andrew, please.
Thank you. Thanks for the introduction, and thanks very much for hosting me here. I've had just coming to the end of 4 weeks in Slovakia, and it's been a great trip. I've enjoyed being here at the university and in Banská Bystrica and in the mountains. It's all in all been a wonderful time. So, as Miroslav said, this is one of the sort of main open problems, and I think what makes it such a tantalizing problem is the fact that it, like many open problems, it seems so simple, and many of the methods that have been used are quite simple, and yet still there's no answer to it. But we have some ideas, and that's why I thought I would speak about it today. Yeah. So this is the statement. It says, is every finite lattice isomorphic to the congruence lattice of some finite algebra? And so that and that really leads to the outline for the talk. I think if we're going to understand this problem and enjoy it, then we need to just remember what finite lattices are, finite algebras and congruence lattices, and then once we've been through that, we can look at the work that has been done already, and then some ideas for a new approach to solving this problem. So I'm sorry if some of the early stuff is a little bit elementary, but I think it's important that we are all on the same page, and actually it's the simplicity, like I said, that makes it so interesting. So a lattice is simply a partially ordered set. So we've got a partial order, reflexive, transitive, and antisymmetric, and every two elements have a least upper bound and a greatest lower bound. There is an algebraic definition as well, but this is usually the easiest way to understand. So we can draw them with these diagrams where the order is going from the bottom up to the top. So just to be really thorough here, the least upper bound of A and B will of course be C, and the greatest lower bound will be 0. And in each of these cases, each of these examples, for any two elements, there is a least upper bound and a greatest lower bound. And these two are quite important, especially the middle one. We'll come back to that later on. So just to emphasize that not every poset is a lattice. Obviously, for this poset P, these two elements, they don't even have a common upper bound, let alone a least upper bound. These two elements here in Q have no lower bound. And then R is perhaps the most interesting, where for these bottom two elements, there are two upper bounds, but there is no least upper bound. So that's a partially ordered set that's not a lattice. So where do we see lattices? Well, we actually see them everywhere in mathematics, and the simplest example is probably a power set. If you take a two-element set, then your power set has 4 elements, and the partial ordering that you put on the power set is simply set inclusion. Your greatest lower bound operation is just intersection, and least upper bound will be union. And so we get the 4-element lattice. If we start with a 3-element set, well, then we get an 8-element power set and an 8-element lattice, which is, these lattices in particular are Boolean algebras, but mostly we're just interested in the fact that they are lattices. So we've got partially ordered sets with greatest lower bounds and least upper bounds. Another familiar example of lattices is if you look at the collection of subgroups of a group. So let's take a nice familiar group here, the Klein 4 group. So the 4-element abelian group where every non-identity element is its own inverse. What do we get here? Well, each of the non-identity elements simply generates a 2-element subgroup, and so here we get that lattice that we saw earlier on, the lattice of subgroups. And notice here that your greatest lower bound operation is simply the intersection of two subgroups. However, when you take the least upper bound, you need to take the subgroup generated by the union. And so that's why, for instance, with x and y, when you have the subgroup generated by their union of these two-element subgroups, you just get the whole group. And then another important place in which we see lattices is if we look at the subspaces of a vector space. So here we've got two-dimensional vector space, and I've very deliberately chosen to look at it over the finite field with 4 elements. So this is these finite fields might not be too familiar. These are the operation tables, and then this over here, this lattice is the lattice of subspaces of that vector space. Okay, and you can see it's quite similar to the example on the previous slide. The lattice doesn't have much height; it's only got height 3, but it's getting very wide, and this is an extremely important example for the congruence lattice problem. So these are all the finite lattices of size less than or equal to 7, and you can see here the one with 3 elements across that we saw earlier, and also the one with 5 elements across over there. And of course we've also got the power set lattice over there, the 4-element lattice. So just a quick revision of what I mean when I'm talking about an algebra. I've got a set and a finite set of finitary operations on that set. Of course, familiar examples are groups, rings, and in fact lattices are also algebras, right? If we consider these two operations, we call these the meet and the join, and they satisfy certain laws, certain equations, you can define a lattice as an algebra, and there's an easy way to go between the definition in terms of partially ordered sets and the definition in terms of algebras. And then of course vector spaces as well form algebras if you're taking the vector space over a finite field, and then your scalars become a unary operation like this. And so that's what ensures that you have finitely many finitary operations. And then an important last definition on this is just homomorphism. So those are just operations between algebras preserving the algebraic structure. Very familiar, I'm sure. I'm sure you've seen group homomorphisms plenty of times. So we've done the lattices, just a quick look at the algebras, and now we want to talk about congruence relations. So if we've got an algebra, we're going to look at an equivalence relation on the underlying set of the algebra, and we're going to require that equivalence relation is a congruence if it forms a subalgebra of the direct product of that algebra with itself. So in other words, it's an equivalence relation that interacts with the algebraic structure of that algebra. That's kind of the easiest way of thinking about it. And if you take simply the the diagonal of the product, that is going to give you always the smallest congruence on an algebra, and the largest congruence will simply be the Cartesian product of the underlying set of the algebra. So you've got the smallest one, the biggest one, and they in fact form a lattice. This will be important for us as well. If we've got a homomorphism, then the kernel of that homomorphism will be a congruence on A. So there's a useful interplay there between homomorphic images of algebras and congruence relations. Okay, so when we have all of the congruences on a particular algebra, we define the greatest lower bound to be just intersection, and in the same way as for the subgroups, you define the least upper bound to be the smallest congruence containing the union of the two congruences. So it's the kind of standard way that you would look at a closure operator on a set. And so then the ordering then is just set inclusion. So quite a nice simple structure that these congruence lattices have. So these are just a reminder again of all of these finite lattices. And remember that the challenge of this problem is to represent every finite lattice as the congruence lattice of some finite algebra. Okay? So these are all of the ones just up to size 7. And some of them are distributive, right? What does that mean? It means that these two operations of the lattice distribute over one another, right? So the usual distribution that you've seen in other contexts. And then this important theorem comes from 1962, where Gratzer and Schmidt proved that every finite distributive lattice is isomorphic to the congruence lattice of some finite lattice even. That's just a kind of curiosity, but the point is that you've got all of the finite distributive lattices that are now isomorphic to congruence lattices of some finite algebra. You can ignore the fact that that's a lattice, but what it means is that in this picture we can tick off a whole lot of the finite lattices, right? So all of the ones that I've ticked green, those are all the distributive ones. So those are now taken care of by that 1962 theorem of Gratzer and Schmidt. So you might remember on the very first slide, these two lattices, well, the first slide where I showed examples of lattices, these two occurred. Okay? And what's important about those two is that they are not distributive, right? And so now that theorem can't be applied to those two or to any of these other lattices here. So essentially, when you lose distributivity, the structure of the lattices can be a little bit more wild, and that's what makes it harder to represent them. And something else that's important to observe is that all of the lattices of this form, where you've got these elements in the middle of the lattice that are not related to one another, so here where there are 3 unrelated elements, here where there are 4, and where there are 5, those are all non-distributive. Okay, so they are not covered by the 1962 Gratzer-Schmidt theorem. Right. So now this is a paper from 1963, again by Gratzer and Schmidt, and what they were trying to do was to find representations of algebraic lattices. I won't say what that is, but they were looking for representations of algebraic lattices as congruence lattices of some algebra. Okay? So remember, all along we were interested in representing lattices as congruence lattices of a finite algebra. So they were able to do it. They said, okay, if we're allowed to use infinite algebras, we can get this representation. And then they posed the problem. They said, now, is it possible to represent every finite lattice in the form of a congruence lattice where A is a finite abstract algebra? So that's the problem that we're talking about. And it was a natural thing for them to ask. And sort of in a very kind of understated way, they say here, this problem seems to be an extremely difficult one, right? And here we are, nearly 60 years later without an answer. So I think they were certainly right about that. Okay. So the rest of the talk, I'm going to focus on algebras, on lattices that look like these ones. There are some very nice results, and many people consider this to be the kind of key to the problem. If we can represent those ones, then we can probably do all of them. And if it's going to fail, it's likely going to fail on one of those. And we have some ideas about how to tackle that as well. So, remember the group right at the beginning. This was the 4-element group, and we got a subgroup lattice isomorphic to this lattice here is known as M3 because it has it's a modular lattice with 3 elements here. Okay, but remember, we're not trying to do subgroup representations, we're trying to do congruences. However, this Klein 4 group is of course isomorphic to the direct product of Z2 with itself, right? And what you get here is you've got the direct product of 2 abelian groups. This group is obviously abelian, and in an abelian group, every subgroup is normal, right? So what that means is that the lattice of subgroups is isomorphic. Well, it is exactly the lattice of normal subgroups, and the lattice of normal subgroups, those are kernels of homomorphisms, and therefore congruences. Okay? So that's why I sort of included that statement about the kernels of homomorphisms. So in an abelian group, every subgroup is normal, and therefore your subgroup lattice is simply the congruence lattice. So this provides us with a representation of M3 as the congruence lattice of clearly a finite algebra. And in fact, this can be generalized and is not too difficult to prove. That if you have the cyclic group of order P, where P must be prime, then if you take the product of that group with itself, that will give you a congruence lattice that will be isomorphic to Mn, where n is P plus 1. Okay, so that means that if you think of those lattices with the elements going across the middle, if the number of elements in the middle is a prime plus 1, then you've already got a representation just using the direct product of cyclic groups. So a nice kind of simple way of doing it. Okay, so that would then, so remember it's saying P plus 1, so that will take care of this one because we've got 3 elements in the middle, so then 2 plus 1. Here we've got 4 elements, so 3 plus 1. But what about this one over here? Right? Well, for that we can use the example that we saw at the beginning with our 2-dimensional vector space over a finite field of order 4. Okay? So remember that we had the vector space, and then these were the subspaces. Well, it turns out that in the case of vector subspaces, every subspace is the kernel of a linear transformation, and linear transformations are the homomorphisms when vector spaces are thought of as algebras, and so that means that the subspaces are simply going to be exactly the congruences on that algebra. And so, it's going to be these kernels that will give you these congruences. So this then helps us even further, right? Because if we have p to the k, where p is a prime, p to the k plus 1, then if we let n be equal to p to the k plus 1, then mn, which is that the lattice of height 3 with the n elements in the middle, that is going to be isomorphic to the congruence lattice of the two-dimensional vector space over that finite field. And remember that we only get finite fields for prime powers. So that's another systematic way of constructing congruence lattices for Mn, and of course it's working for p to the k plus 1, and so that covers even more examples than the example with the products of cyclic groups. So then this is quite a big step from those constructions, which covered a large number of examples. Now let's take a look at what's happening here. We've got H being a subgroup of a group, and now we're interested in the interval in the subgroup lattice. So I'm using that bold face, sorry, the blackboard S to denote the subgroup lattice. And so this is all of the subgroups, obviously, greater than all of the subgroups that contain H, and going all the way to the top, to the largest subgroup, which is G itself. And then we remember that every finite group can be thought of as group permutations. And again, this is a really important theorem, but not one that's particularly difficult to prove if you have some experience with basic abstract algebra. So what it says is that if you've got a lattice isomorphic to an interval in the subgroup lattice, so in other words, you need to have your group G, you need to find a subgroup H, look at the interval of all the subgroups above H, and if that's your L, well then what you can do is you can construct an algebra A such that L will be isomorphic to the congruence lattice of A. So what this is doing is it's really transferring the search for representations of finite lattices as congruence lattices of kind of any abstract algebra. It really transfers that problem to a problem about understanding what the subgroup lattices of groups look like, which is, there are books written on this topic, and it is a field of much study, and this really got people quite excited because they thought, okay, we know a bit about subgroups of lattices. If we can apply what we know, then maybe we can use that to solve this problem. And so this is the construction. It's, as you can see, it's quite simple. We simply take these left cosets and define a set of operations like this. They're all unary operations, and then you can get L isomorphic to that congruence lattice. But it's really all about first identifying L as an interval in this subgroup lattice. So here's an important theorem, right? Remember we had p to the k plus 1 taken care of for those lattices of height 3 with n elements in the middle. So that covered M3, M4, and M5, as well as M6. But M7 remained unsolved for many years until Fake came up with this result in 1983, where he identified a group, so the alternating group on 31 elements, and then found a subgroup H of order 155, such that M7 was isomorphic to that interval in the subgroup lattice. So all of the subgroups bigger than this subgroup with 155 elements going all the way up to A31. So what does that then mean? Well, it means that M7 is going to be isomorphic to the congruence lattice of an algebra with 30 factorial divided by 10 elements. Okay. So things were nice and comfortable. We could use our vector spaces for the M3, M4, M5, and M6, and then suddenly we get to M7, which is just a 9-element lattice, those 7 elements in the middle, the top and the bottom, and we've got this completely wild algebra. It works, but it's it took people a long time to find. So and then the comment as well is that this approach doesn't extend beyond this. It was quite an isolated example. It works for n equals 5, 7, and 11, but using alternating groups, no other results were obtained. So earlier we saw that if you could identify L as being isomorphic to this interval in the subgroup lattice, then you can build an algebra such that L will be isomorphic to the congruence lattice of that algebra. But this is an important theorem that says these following two statements are important. So every finite lattice occurs as the congruence lattice of some finite algebra. So that's the big problem, right? That's the question we want to know the answer to. That is going to be true if and only if every finite lattice occurs as an interval in the subgroup lattice of some finite group. So what's important here is that it's not saying that for individual lattices they are going to be representable if and only if. It's saying it must happen, it either happens for all of them or not, right? So if this is false, then this statement is false, which means that there's going to be some finite lattice which doesn't occur as an interval in that subgroup lattice. So again, this result really got people even more intensely interested. And there are some further results that again focusing on these modular lattices with n elements across the middle. These proofs, I haven't read them in depth. They do extend the earlier results, but of course the techniques are a lot more complicated. What's so nice about the ones involving cyclic groups and the ones involving vector spaces is that with a very simple technique you're able to solve a large number of examples. So this is saying that for n equal to q plus 2, where q is prime power, or if you can get n equal to q to the t plus 1 over q plus 1, all of that plus 1, in those cases, mn is taken care of. Okay? So what does this give us? Q plus 2 takes care of many values of n, and this second expression also takes care of many values. However, M16 and M23 are not covered by this, okay? and are not covered by any of the previous theorems. So here we've got what looks like a relatively sort of simple lattice. In a sense, it's just 16 elements across, the top element and the bottom element, top element and the bottom element. No known representation is available. And then some more recent work. I mean, that was 1994, and it was kind of around that point that the group theorists almost, they tried and eventually got stuck. A PhD thesis by William DeMayo in 2012 returned to the problem. So this lattice on the right-hand side is interesting because it is representable as a congruence lattice, but at the moment it has no known representation as an interval in a subgroup lattice. Okay? So an algebra has been found, but not going via that subgroup lattice method. And then this 7-element algebra, this 7-element lattice on the left, has no known representation within intervals and subgroups or as congruences. So, I mean, there's M16, which is a very, it has a very simple structure, but it has 18 elements, that it has no known representation, and then this 7-element lattice is the smallest lattice without a known representation. So maybe to end with some ideas about how we hope to attack this problem. Of course, clever people have worked on this for almost 60 years, so we shouldn't think that we are going to solve it or even necessarily make some progress, but it's just so tantalizing. It feels like we've got to try. You know, everyone's got to dream big. And the idea here is based on a dual representation of finite lattices via finite digraphs, which I'll now explain. So here are a couple of finite lattices, and again the idea here is really quite simple. We've got filters which are upsets of the lattice that are also closed under meets or closed under greatest lower bounds, and then we've got ideals which are downward closed sets in the lattice, and they are closed under joins or least upper bounds. And then what's important here is that in finite lattices, every filter will simply be the principal upset of an element. So that up arrow A just means all of the elements of the lattice greater than or equal to A, and then down arrow B, all of the elements less than or equal to B. So if we take a look at some examples in a second, the important ones that we're interested in is we are interested in pairs where you've got a filter and an ideal that are maximal in being disjoint from one another. So let's take a look at what that means. So for instance here you've got the filter and the ideal. They are certainly disjoint from one another and maximally so, right? You can't add anything to either of them. In this case, you've got a filter that is disjoint from the ideal, but this is not a maximal disjoint filter-ideal pair because you could extend this filter to be the upset of this element here. That element would still be left out because you wouldn't be able to extend either the... that element could be included if you extend the ideal. So you can extend the ideal to that element, extend the filter down to cover those four elements, and then you would have a maximal disjoint filter ideal pair. And then these two examples here, here we've got a disjoint filter ideal pair that is maximal, and some elements are going to be left out because you can't include that element in either the ideal or the filter. And so then what we're going to do with these is we're going to use a representation of lattices due to a mathematician from Košice, Miroslav Košice. And the idea is that you take a lattice and you take its set of maximal disjoint filter ideal pairs. That's going to be the underlying set of your dual representation. And if you want to think about something familiar, if you're familiar maybe with Stone's representation theorem for Boolean algebras, there you take the Boolean algebras and you take the ultra filters, and that forms the underlying set of your dual space. It's a similar approach. I'm sort of slightly changing the setup just because it's easier, but the idea is the same. So then what we do is we take that set, and in his case he put a binary relation on the set and a topology, and then we're able to recover the lattice from that set with a binary relation and the topology. That's all you really need to take from here, and it's a generalization of some other representations of lattices. So this is the idea. If you've got this set of maximal disjoint filter ideal pairs, then you put this relation E on them, where you say that this first pair Fi is going to be related to the second pair Gj if the filter of the first one has an empty intersection with the ideal of the second one. And so this creates a directed graph, right, on the set of maximal disjoint filter ideal pairs. So let's take a look. We start with this non-distributive lattice N5. So this is a maximal disjoint filter ideal pair. I'm just writing it as AB to say that the filter goes up from A and the ideal goes down from B. We have this pair over here that we saw already on a few slides ago. And then we finally have this third pair. So what we have is three elements of our dual structure. And then we add the arcs to this digraph according to the rule that you saw on the slide before, which says that there's going to be an arc from the one to the other if that filter and that ideal are disjoint from one another. And that can be rephrased as saying that the element that generates the filter is not below the element that generates the ideal. So in this case, we get a very nice simple digraph that represents that 5-element lattice. If we take this example here, this 5-element modular lattice that we've seen quite a few times, what do we get? Well, you can see that if you take any one of the elements in this anti-chain in the middle, if you take the principal up set at one and the principal down set at the other, you get this maximal disjoint pair, and you can do that in 6 different ways, right? You just swap the element that generates the filter and the element that generates the ideal, and you're going to get these 6 different maximal disjoint filter ideal pairs, and then you get the graph structure that looks like this. So this is your dual diagram. And what bothered us at the beginning, well, I mean, this is all just applying Ploszczyz's setup to finite lattices, is that this, you know, on the previous example, we had such a nice, simple digraph, a really efficient representation. And so it kind of seems like, well, now we've ended up with a dual representation of this lattice, which has more elements than the original lattice, which seems like that's not a great way to be doing things, but it might turn out to be useful. So just a remark, if you know the Birkhoff's representation, which is this one-to-one correspondence between finite distributive lattices and finite posets, that is simply a special case of what we get here. So this was Birkhoff's theorem giving a one-to-one correspondence between finite distributive lattices and finite posets. So what it means is that if we do this construction due to Ploszczyz, we then, if the lattice we started with was distributive, the digraph that you get is actually just a poset. So it's a nice kind of well-behaved structure. Okay, so the whole time I've been saying, well, we're getting a representation of lattices. How do we actually get the lattice back? And this is quite a neat sort of trick. If you've got this lattice N5, it's called N because it's not modular. We've got this 3-element digraph, and now the way that you recover the lattice is you consider the set of maximal partial edge-preserving maps from this digraph into the 2-element chain, right? Thought of as a digraph. So a loop on each vertex, and then one arc from the 0 to the 1. So what that means is that you are defining functions on this set going into this 2-element set, which needs to preserve this set of arcs, but you're not requiring that they're total functions. They can have a partial domain, but that domain does need to be maximal. So if we look at the kind of process of recovering this lattice here, well, there are kind of 2 obvious ones. You can remember that you're mapping elements of the set here into the set containing 0 and 1 over there. So you can map everything to 1 or everything to 0. That works fine. You can also then map the bottom element to 0, the middle element to 0, and the top element to 1. That works fine. Or you can map the bottom element to 0, and then the other two elements to 1. But then the interesting one occurs here, where what if you map the bottom element to 1 and the top element to 0? Well, then you can't map the middle element to anything, because then you would break the edge-preserving property of your map. And so then you simply have to leave that middle element out of the domain of your map. And so that's why you would get a strictly partial map over there. And then this, you use this ordering, where for these maximal partial maps, you order them according to the inverse image of 1, just using set containment there. And now you've recovered the lattice that you started. And so this works for all finite lattices. That comes from Kloostert's already. So as I mentioned, here are two examples of non-distributive lattices where you get quite different, differently behaved dual digraphs. And this, with some joint work with Miroslav and then a colleague in Portugal, we were able to identify exactly the properties of those dual digraphs. So I won't really speak much about this, but what was nice was that we were now able to describe those dual digraphs perfectly, and therefore start to study them. And in fact, what we get via this description is we get a generalization of Birkhoff's representation. Remember, his was between finite distributive lattices and finite posets, and we were able to show that if you just consider finite lattices here, so you're not requiring distributivity, then there's going to be a one-to-one correspondence with these finite TIRS graphs. So we had a really precise description of these graphs. We were then able recently to kind of shrink the class again. So we went from distributive to all finite lattices, and then we said, well, let's look at something in between. And so we studied semi-distributive lattices, which are interesting because all free lattices, so the free objects in the class of lattices, those are known to be semi-distributive. These are just some examples. So what makes them quite interesting is that these two kind of very important examples of non-distributive lattices, the one is both join and meet semi-distributive, while the other one is neither of those. And so this theorem comes actually from, it'll appear later this year, myself and Miroslav and a co-author in Sweden, where we describe, again, exactly the dual digraphs that occur via this construction if you start with some kind of semi-distributivity. Okay, so how does this help us? Well, one of the methods for getting congruence representations of finite lattices is that first, remember a congruence relation is an equivalence relation to begin with. So the first step is to identify a set where your lattice can appear as a subset of the partition lattice of that set. And these ones, it turns out, although they're graphs, dual digraphs are kind of messy, they provide a really useful set of elements of their dual digraph. So if we take the dual digraph of one of these Mn lattices, where that n has to be prime for now, then we can get an embedding of that lattice can be embedded in the partition lattice of this set. So ignoring the graph structure for now, just consider these 6 elements that you get as the underlying set of your dual digraph, and we're able to embed for n prime, we're able to embed that lattice in the partition lattice. So now you've got a partition lattice on a set. You need to add some algebraic structure in order to make it an algebra and therefore get the congruence representation. But this provides a very useful starting point. So like I said here, we can represent this lattice within a partition lattice. And then for small examples that we've looked at so far, we can again do this MP plus 1 as the congruence lattice of a unary algebra. So it's nothing new on the examples we've looked at now, but it does provide an alternative method. And what we've been able to show for some of the MNs that are not P plus 1, we can get the embedding within a partition lattice, which is the first step towards possibly getting a finite algebra whose congruence lattice will represent that lattice Mn. So here, the starting point in each case is that dual digraph. And I don't want to say we completely forget the graph structure, but really what's important is the underlying set to begin with, that set of maximal disjoint fault ideal pairs. And then we rely on the graph structure to get the exact detail of the partition representation. And then the other thing which we are busy working on is relying on that 1962 theorem. Remember the theorem that said that every finite distributive lattice is representable as the congruence lattice of a finite lattice, actually, in that case. That theorem uses Birkhoff's dual representation for finite distributive lattices. So it takes the finite distributive lattice, takes the poset dual to it, and then builds the algebra from that poset. And so the idea here would be to do the same thing. That we can take the underlying set of that dual digraph, which we know to be a TI-RS digraph, except we have to be a little bit careful because we need to define algebraic operations on there in such a way that the congruence lattice is not going to be distributive. We don't just want to end up representing distributive lattices again. So the idea there is to use these, to use the graph structure, use the fact that we've got these arcs, and use the arcs to define unary operations, which will then generate congruences. So this is really very kind of fresh. I mean, we're playing with small examples to try and get it to work. The primeness is still a problem. You know, there's a reason that other people were able to more easily represent the lattices where you had, you know, prime power plus 1 number of elements in the middle, or maybe prime power plus 2 even. Yeah, so we're still trying to work on how to overcome that. And it's certainly going to involve quite a lot of computational tools, because checking these things becomes quite difficult. You know, if you look at that M3 example, the dual digraph has 6 elements. When you go to M5, the dual digraph has 20 elements. It starts to get quite tricky, but yeah, I mean, fortunately, they're still finite, and the computational tools are available. And then lastly, I should just end with this quote. I'll give you a moment to read it quickly. So yeah, I think that's some useful advice. I listened to an interview with another well-known mathematician, and he was very excited about the PNP problem, and he said he allows himself 1 hour per week to think about it, and that's all, because he knows if he lets himself do any more, then he will neglect his other work. So I think, as excited as we are about perhaps adding some new tools to trying to solve this problem, we also just have to be cautious. So thank you very much.
Thank you very much, Andrew, for a nice talk and advice to young people. It's time for discussion, remarks or questions. Could you possibly go 2 slides back? Yeah. Here, I would like to remark that what is the idea using this Ploštica approach to make it more precise that by Ploštica we can represent finite lattices as these maximal partial morphisms. Yeah? But and morphisms means we preserve those arrows in the graph. Okay? And so the idea is that if we could replace the arrows with unary operations, that's what many algebras actually do. Or if you look on monounary algebras, there you have those arrows, yeah, and it represents monounary algebra. So if we could somehow represent the arrows by maybe, well, unary operations in the way that these morphisms as arrow-preserving maps would be exactly these operations, unary operations preserving maps, yeah, then we would represent by Ploštica, by this modified version, finite lattice as the lattice of algebra homomorphisms. Okay? And we know that the kernels of homomorphism are congruencies. So if these kernels would somehow follow the structure of the homomorphisms, then we have a chance that as the lattice is represented by algebra homomorphism, maybe it would be represented by kernels as the congruencies. That's the idea. It's a very fresh idea, but maybe it could work actually. So the algebra wouldn't be very nice. It wouldn't be two-dimensional vector space or abelian group, but so it would be more combinatorial solution to the problem. Yeah. So that's somehow to make that last idea a little bit more precise. Yeah, I believe it's combinatorial, and not group theoretical. Yeah. Some people say that it's group theoretical problem and the answer will be negative at the end. But I'm positive and believe it will be positive and it's more combinatorial. The algebras will not be nice, but that's what Gretzer Schmidt had. Their algebra is horrible. It's very wild algebra, but it works. Yeah.
Can I have a little, perhaps a few questions from a complete outsider of the field? So first of all, thank you very much. It was very brilliant and engaging talk, like showing us the advances of your research collaboration with Miroslav. So this was really nice to see. I'd be interested to what extent the computational tools are being used in your research, and will just give us some idea how you solve these kind of problems, whether you're making use of some kind of powerful supercomputers or something like this.
I mean, it's nothing like that. It's mostly so with this one here. The idea here is that you represent the lattice initially as some partitions on a finite set in this lattice of equivalence relations, and then you need to check which unary maps on that set preserve those relations, and then if they preserve any other relations. So it's the computational power is not really an issue. It's more using the programs to kind of check if your conjecture is right, and if not, find out where it's
Whether
breaking.
it makes sense to proceed in that.
Yeah,
particular
because
direction.
ultimately, I mean, we're trying to do this for all finite lattices.
Yeah, sure.
And at the moment, what makes these MNs nice is that even the dual digraphs, like I was saying, there's a large kind of growth in the size of the number of elements, but it's at least got this kind of regular structure, so you know a little bit what to expect there. But yeah, it's not like we're sort of just sending these things out in some vast search space to try and
And a completely different question could be that suppose that some advances could be done along the directions that you do, or suppose that even the whole problem would be kind of solved. One part is the aesthetical appeal of the whole problem, and would it even have some kind of applications for industry, or for some, or would understanding or solution to this problem would kind of help in some kind of concrete or practical problems as well?
I wouldn't imagine in any kind of concrete practical problems, but I mentioned the PhD thesis of DeMeo from Hawaii, and he phrases it quite nicely there, where he says that at the moment we don't know what the congruence lattices of finite algebras look like. We know that some lattices occur as these congruence lattices, and if you can't make some sort of all-encompassing statement about the congruence lattices of finite algebras, then it's saying that you don't really understand all finite algebras, which, I guess that's one of the motivations, that the congruence lattice is somehow almost like a signature of the algebra. I shouldn't use the word signature, like the fingerprint of an algebra.
It's an excellent answer. Thank you.
But,
Yeah, he makes very strong statement. We teach algebra, but he says, until this problem is solved, we don't understand finite algebras at all. You cannot say we understand them.
In the beginning, you said that solving the problem for those lattices is like minimal element, few elements and small elements, will be like the key to solving the whole problem. Could you elaborate why is it so?
Yeah, I think it's mostly so on the negative side, in the sense that if it's to find a counterexample in the space of all lattices, where do you start? Do you choose a 13-element one or a 25-element one? Whereas there, because already at small sizes, people have had to find special ways of, there's this systematic way, but then it doesn't work for this value. It just feels like if a counterexample is going to be found, it'll be found there.
Okay, so let's thank Andrew again. And I'd like to thank also to Lukáš for picking up the flag again, and hopefully the seminar will continue. And so we look forward to the next seminar in several weeks, I reckon.
Yeah, please check Akasim Krasnodar.
Okay, so thanks again for coming, and have a nice day.
Thank you.